This is Science Max, Experiments at Large. Science Max! It's time to get stuck on magnets. What's our attraction to magnets? What's their attraction to each other? And can I use magnets to levitate and float in the air? All on this episode of Science Max, Experiments at Large.
Greetings, Science Maximites. Welcome to Science Max Experiments at Large. My name is Phil, and today we're going to be looking at the power of magnets. You see, magnets are fun things to experiment with because they are really, they're really interesting. This magnet that I've got here is a neodymium magnet, or a rare earth magnet. It's one of the strongest magnets you can get. A magnet is an object that is attracted to anything that is ferromagnetic, which is iron, nickel, or cobalt. And magnets are interesting because they have two sides. There are two poles. I'd show you, but I can't get the chain off. Hold on one second. Ha-ha! There are two. Oh, no. There are two poles to every magnet, just like the Earth. There is a North Pole and a South Pole. That's right, the Earth is a giant magnet. So, if you take kitchen magnets, you'll find that there's two different poles. I've written north and south on these ones. They don't normally come like that. If you put the north and the south together, they stick. But if you put the north and north or south and south together, they repel. They repel, see? They don't want to go together at all. And you can force them together if you want, but if you do, they will spring away the second you let them go. Whee! But when magnets repel each other, I find that some of the most interesting stuff. Check this out. This is just a small container, and I've got a magnet in here, and I have a loonie attached to it so that it fits nicely in the container like that. For the top, I've attached two magnets together, and I have another coin on it. And if you put them in there, I've made sure that the two poles repel each other, which means this magnet will just sit there and float. Magnetic levitation. Very interesting. And you can pop the top on that if you want and just carry around a levitating magnet. Now, there's a couple fancier ways you can levitate stuff with magnets. This is just a wooden frame I've made. This is completely not necessary. You can use just about anything in your house. A desk lamp works really well. The important part is I've tied a magnet to the end of this arm here, and this is a bolt, which is attracted to the magnet, but it's got a thread tied to it, so it can't get there. Just far enough that it will actually hang in mid-air. Look at that. It's not attached to anything. It's just being pulled up by the attraction from the magnet. The thing is, as soon as you pull the bolt away far enough, it will lose the attraction and it'll just fall. Very cool. Here's one that's a little bit more complicated, but is also really neat. This one uses disc magnets, which have a circle or a hole in the middle of them here. And you put two around a pencil and then four more in such a position that you can put the pencil against this wood on the side and it will just levitate on its own. You can even give it a spin. Look at that.
And if you want to make a levitating pencil yourself, there's step-by-step instructions on how to build an easy-peasy version on our website.
Meantime, we are gonna max this out. Magnetic levitation on Science Max Experiments at Large. But you're probably thinking, what are we going to levitate? Well, we're going to levitate me. At least, that's the plan. That's why I'm going to the Center for Skills Development and Training. Come on.
Okay, who turned out the lights? Guys, ow, what was that? Why is this room so small? and only going down to waist level. This is the weirdest room I've ever been in. Where am I? What's going on?
Hey, Matt.
Hi, Phil.
This is Matt. He's from Jobmaster Magnets. Now, you guys use lots of big magnets, right?
That's right, we do.
Awesome. So maybe you could help me max out this.
Wow. You did a great job of building the levitating pencil experiment.
Yeah, so what's going on here exactly?
Well, all magnets have at least a north and a south pole.
Right.
And when you put like poles together, they want to repel.
Oh, okay. So have you ever levitated a person?
Not yet.
Well, let's do it.
All right.
Do you think we can use these?
We can try.
Okay, well, put that one on the ground. And, okay, so north, and I'll put the north one on my foot here. And then if I just step, oh, wait a minute. If I step, stop moving. If I step on the, okay, well, first of all, this magnet keeps sort of moving away from me when I try to push down on it. What do we do? How do we fix this?
Well, we need to keep the magnets in position so that they don't move around when you try to bring them together.
Yeah, because I have to come straight down on it, don't I?
That's right.
So why don't we attach this one to the floor?
Good idea.
And then we'll put a board on this one, and we'll see how it goes.
Perfect.
Okay, let's do it.
All right.
This is a magnet. This is a magnet. This is a magnet. This is a shoe. What's the difference? To know that, you have to know your magnets. This is a donut. It does not stick to this magnet. This is a spoon. It sticks to this magnet. These paper clips stick to this magnet. This shoe does not. So what is attracted to magnets? Only things that are ferromagnetic. Here's the difference. Horseshoe, horseshoe magnet. This one is a magnet. This one is not. But the horseshoe sticks to the horseshoe magnet because this one's a magnet and this one is ferromagnetic. Only things that are ferromagnetic are attracted to magnets. Things that are not attracted to magnets, they're not ferromagnetic. Plastic, banana, mitten, sandwich, magazine. No, but how do you know? Do you go around the world sticking a magnet to every single thing one at a time? Hey, Ma, I need you to come over. I need to see if you're ferromagnetic. No, ferromagnetic. No, you don't need to do that. First of all, only metals are ferromagnetic. So that eliminates all your clothing, your luncheon meats, your magazines, what have you. Everything that's non-metal, you don't need to worry about. Never mind, Ma, it doesn't matter. But this clock is metal. It doesn't stick. Well, not all metals are ferromagnetic. Mainly just the ones with iron, nickel, or cobalt. And there you have it. Now you know your magnets. I hit the phone on the magnet there. Can you hear me, Ma? Hang up the phone. Hang up the phone, Ma. My first attempt at levitating had the magnet sliding all over. So the plan is to take the bottom magnet and attach it to a big wooden board so it won't go anywhere. Then attach another plank to the top magnet to make it a little easier to stand on.
Okay, that is definitely attached to the floor. Thank you. All right, now, if I just get this lined up, whoa, look at that. You could totally, oh, wait a minute, totally, it doesn't want to stay put. Oh, wait a minute. They levitate. Come on, levitate. Why doesn't it want to stay? It just doesn't. Should I stand on it? Okay, I'll stand on it. Here we go. And am I levitating?
No.
No. So why isn't this working?
Well, just like your pencil experiment, we need a shaft through the center to hold the magnets in position.
Oh yeah, maybe we could use like a ring magnet.
Yes.
That like we used with the pencil.
Right.
And
And we're gonna need stronger magnets.
we're gonna need stronger magnets. Are the ring magnets strong?
Yes, they can be.
Awesome. All right, let's do it.
All right.
Now it's time for a Science Max quiz. Which one of these things do we have magnetism to thank for? Birds flying south in the winter, music, or a sandwich? If you picked A, you're right. Some birds migrate in the spring and fall using the Earth's magnetic field. Many animals can sense the Earth's magnetic field and use it to navigate. Migrating birds fly hundreds or thousands of kilometers north or south when they migrate in the spring and fall. A compass works the same way, by using magnetism to point to the Earth's magnetic North Pole. But if you picked B, music, you're right! Here's some music. The way you're hearing this music is because the musicians recorded their instruments using microphones, which use magnets. And then the signal was translated by a computer and stored on its hard drive, which uses magnets. Then it was broadcast to your TV and comes out your speakers, which use, you guessed it, magnets. And for those of you who said you have magnetism to thank for your sandwich, haha, well, you're right. You see, you'd probably go to the kitchen to make that sandwich, right? Well, I'm guessing you got all of the tasty ingredients from your refrigerator? Well, it works on electricity, which is produced by magnets. And then there's an electric motor in the fridge that circulates the air and keeps it cool. And guess what? Magnets. And finally, the door on your fridge stays closed because the door has magnets. So there you go. You can thank magnetism for birds flying south, music, and your sandwich. It just goes to show, when you're talking about magnets, everybody wins because magnets are everywhere. This has been a Science Max quiz.
Mini Max.
Here's an experiment you can do with a bag of water. Take a sharpened pencil and carefully push it through the bag. If you do it carefully, it won't spill. The reason this works is because the bag is made of polymers, long stretchy chains of molecules, and also because the pressure of the water against the pencil prevents any water from spilling out. Now, we're gonna max it out. This is a very large bag of water, and here I have some very large pencils. You ready? Oh. That's one. That's two. Here we go. Should I go from the bottom? Ta-da! Science! Okay. I know what you want. Like I was saying, science! Turns out trying to balance two repelling magnets on top of each other is pretty much impossible. Here's why. This is a magnet, and here is the magnetic field. It's often drawn with lines like this, but actually the magnetic field radiates out in all directions. Really, think of the magnetic field kind of like a ball. When you try to balance another magnet on top of the first magnet, it's about as hard as balancing one ball on top of another ball. So here's the plan. Just like the levitating pencil, we're going to use ring magnets because we can put a shaft through the center of one ring, then drop another ring magnet on the shaft. It will keep them perfectly aligned. Then it's just a matter of putting the bottom magnet on a board to keep it stable and using another board so I can stand on it, and ta-da! Magnetic levitation! Or at least that's the plan. Okay. Board.
Magnets.
Magnets. Ooh, look at that. Awesome. And now I'm gonna put the platform on. Nice. I got some weights here. Let's see how this works. Yeah. This is gonna work amazing. All right, think I should try it?
Give it a try.
Okay. Here we go.
Yeah! I'm doing it! I'm levitating! What?
Just a little bit.
Oh, really?
Yeah.
So, yeah, what do we do?
We need more power.
More power? I like that idea. How do we give it more power?
More shafts, more magnets.
Okay, sure. Well, why don't we do 1, 2, 3, 4 shafts, and then we'll have magnets on all the shafts.
Great idea.
All right. Let's do it.
Mini Max.
If you attach something ferromagnetic like this washer to a magnet, not only does it stick, but the magnetic field travels down the metal, making it a magnet too, which means you can stick more and more things to each other, and they will continue to stick until you run out of magnetic field. You can do this yourself at home with anything ferromagnetic. Paper clips work pretty well, or washers like I have, or screws, or bolts, and they'll continue to stick to each other as long as the magnetic field is strong enough. You can see it's getting pretty weak here. And they'll all stay magnetized as long as the first one is still attached to the magnet. But if you want to go even further, all you need to do is keep adding more magnets to reinforce the magnetic field. I've got a few here like this. Get the chain started like that. And then I've got a magnet attached to this washer, so it will keep the magnetic field strong. And I continue to add one magnet, one washer, and we'll just see how far I can go. You can even sculpt it a little bit. Look at that. And then at the end, a whole bunch of paper clips. Eventually, the weight will make it fall off, but it's a lot of fun to play with magnets and make art. Speaking of art you can make with magnets, you can also make sculptures. When everything sticks to everything else, you can make some pretty fancy designs. This is a rare earth magnet, a very strong one, and a bunch of nuts that I've gotten. And this one here is an electromagnet, but electromagnets are a little different because they need an electric current to work. Check this out. This is sort of a magnet dude with crazy hair. There's an earth magnet here, and this is a giant screw, and these are some metal bits, and then I've got 2 more magnets at the top here to hold on his crazy wire hair. He's got crazy wire hair because he's crazy magnet dude. Now, of course, we couldn't just talk about magnetic sculptures without maxing it out, so let's max it out. This is a bunch of scrap metal from leftover experiments, and I've got a bunch of rare earth magnets, and now I'm gonna max out a magnet sculpture. Let's see. There you go, a maxed out magnet, me! I made this guy out of metal pipes with earth magnets in between, and these are his arms attached, of course, with magnets. His hand, his little metal pieces attached with magnet. Steel wool for the hair, and of course, hat, non-magnetic. All right, here we go, ready? Want to see a magic trick? Simple copper tube. Drop things through it. Nothing unusual happens, but watch when I drop a magnet through. What? It's not magic, it's science. Because the magnet creates a magnetic field, when it goes through the tube, the magnetic field repels the magnet upwards. Now, the field isn't perfect, so the magnet doesn't come to a stop, but still, it slows down from a fall to a nice, graceful drop. Take a look from above. Pretty amazing, right? Magnets. Not magic, science.
So I've managed to levitate on some magnets, but just barely. What Matt and I needed was more power. So instead of having one shaft and one pair of ring magnets, we're going to use a larger board and put a shaft on each corner. Then we'll have 4 times the power because we're using 4 times the magnets. Hopefully this will be strong enough to get me floating on a cushion of magnetic energy.
And magnets?
Magnets.
Okay, here we go. This is gonna work great. And top board. Ooh, what do you think?
Looks great.
Yeah. Okay, here we go. Matt?
You're levitating.
I'm levitating! Woohoo! All right. It feels cool. It sort of feels like surfing a little bit. All right, thank you so much, Matt. That was amazing. And there you have it. Science Max, experiments at large, magnetic levitation. You know, I'm surprised we could do an entire episode on magnets, and we never actually got them so close to the camera that the camera went all weird, because cameras and magnets, they don't, oh dear. No, that's okay. I can fix this. If I just maybe, no. Maybe if I put the magnet to the camera again, that would, okay, that's not, that didn't help. Oh, okay, well, thanks very much for watching Science Max, Experiments at Large, and we'll see you again as soon as we get into the camera.
Electromagnets are magnets you can turn on or off when you want. We build our own electromagnet and see just how powerful we can make it.
It held 100 kilograms.
Plus ferrofluid, wizards, and I tried to get to the North Pole using a compass.
Now that I'm here, I realize it's really difficult.
All on this episode of Science Max, Experiments at Large.
Greetings, Science Maximites. My name is Phil, and welcome to Science Max, Experiments at Large. At this very moment, half the lab is being held together with the power of electromagnets. Magnet 1 turning off. Electromagnets are a really cool and powerful way to interact with the world. And when I say power, that's because you need power to make them work or not work. Magnetism is an invisible force that has to do with the magnetic fields created by magnets that lets them attract things that are metal or each other. But electromagnetism is a little different. You see, magnets are magnets all the time. It's because of what they're made out of. Electromagnets are only a magnet when you have an electric current going through them, which means you can turn them on or off. Today, we're gonna be building an electromagnet. Oh, that was the wrong switch. Anyway, like I was saying, today we're gonna be building an electromagnet.
You need a bunch of copper wire, a very large nail, or something metal to become your electromagnet, electrical tape, a battery, an on-off switch, wire strippers or a craft knife, and the help of an adult, and finally, something to magnetize, like these paper clips. And remember, all of the steps for this experiment are on the website. To begin, take the copper wire and start at the top of the nail. Leave a little bit of wire sticking out, then carefully start to wrap the wire around the nail. Don't go all the way to the end because you need some metal to turn into the magnet. Instead, when you want to start again, run the wire straight back to the top and start wrapping again in the same direction.
And keep wrapping and wrapping until you get to this. Now, I've used some electrical tape here, here, and here to hold it all together.
Using your wire strippers or a craft knife and the help of an adult, remove the plastic coating from the ends of the wires. Attach these wires to the wires from the on-off switch with electrical tape, or attach them directly to a battery if you don't have an on-off switch.
And ta-da, you have an electromagnet with your on-off switch. All you need to do is take the things you're going to magnetize, turn your electromagnet on, and suddenly it becomes a magnet. Pretty amazing. And then you can magnetize to your heart's content. But when you're done, don't forget, you want to turn it off. So that's what we're gonna do today on Science Max, Experiments at Large. We're gonna max out the electromagnet. So, where's my lab coat? Oh, there it is. We're gonna see how big we can make an electromagnet. And when I say we, I mean me and an expert. Let's see. Oh, Heather from the Ontario Science Center. She knows her way around magnets. So let's see. Yeah. I wonder if she's busy. Well, let's find out.
And after we're done, I'll need to come back and clean up the giant mess I made in the lab.
Hey!
Hi, Heather, how are you doing?
Good to see you, Phil.
I was just wondering if you could help me with something. Are you busy?
No, I got time.
Okay, great, because I'm gonna make a giant electromagnet experiment and I need your help.
That sounds like a lot of fun.
Okay, great. Let's go back to Science Max headquarters.
Oh,
we'll
via
take
the portal?
Yeah, by the portal.
Oh, okay.
You sure? I
Yeah.
know you're hesitant, so I want to reassure you, nothing will go wrong.
Great, okay.
Okay. Oh, hey, we're here.
It's
okay, it's okay.
No,
Don't worry about it.
no,
No,
I
no.
think
It's fine,
definitely.
it's fine.
You all right?
Yeah, I was supposed to come in over there, but I came in over here. Oh well. So today, Heather, I want to max out the electromagnet. Turn it on, and it's a magnet.
Pretty good.
And turn it off, and it stops being a magnet. I want to make this into a much bigger, maxed out version.
All right.
So what are some of the things we can do to do that?
Well, actually, if you have a larger battery, one that has a higher voltage, we can try that for sure.
Okay,
that
so
will help.
there are batteries that are 12 volts?
Yes.
We could try one of
Give it
those?
a try,
I think
for
those
sure.
are like bigger, right?
Yeah, bigger, more powerful, absolutely. Now, that's one thing you could do. You could also increase the number of wraps of our coil here.
So how many times we wrap that wire?
Yes, we'll increase that magnetic field, making our magnet stronger.
And of course the nail, which is important because that's the thing that eventually becomes the magnet, right?
Right on, yes.
So what I thought we would do is we would start with a bigger nail.
Oh.
What, right? So larger battery,
Yes.
more voltage, and a lot more wraps of the wire.
Right on, and we have more space for that now, which is smart. Good job.
Great, okay, so we'll get to work.
Great.
Max Historica.
If you've ever seen a compass, you know that the needle points north. That's because a compass needle is a magnet and it points towards the Earth's magnetic North Pole. And I'm using this compass to try to get to the North Pole. But it isn't easy. In fact, scientists knew there was such a thing as the North Pole as far back as the 16th century, but no one was able to actually get there on foot until 1927. You'd think it wouldn't be that hard, right? I mean, the needle points you straight there. Just follow the needle, right? But now that I'm here, I realize it's really difficult. I mean, the wind is incredible and the snow is intense and it's so cold. My hands, yeah. So, okay, we're not really at the North Pole. We were just sort of recreating that. But still, I salute the brave explorers who tried to make it there in the name of science. And I got a sense of it because the wind from the fan and the fake snow was. Okay, everybody, let's pack it up. I mean, that was pretty good. I just didn't know about that other camera.
So, back to our main experiment, where Heather and I are building a larger electromagnet. An electromagnet works like this. When an electric current is traveling through a wire, it creates a magnetic field. If you wrap that wire around something ferromagnetic, that's something made out of a metal that is attracted to magnets, like an iron nail, then it becomes a magnet. You can make a magnet stronger by wrapping more wire, which gives more distance for the current to travel, increasing the magnetic field, and you can also increase the strength of the current. Heather and I start with a coil of 30 meters of wire and start wrapping. And wrapping. And wrapping.
There, the wire is now all done. And remember, if you're doing this at home, do not use a drill unless you have an adult to help you out because drills can be very dangerous. This one goes at a very slow speed, so it was okay. But yes, definitely an adult supervised activity.
Then we attach another on-off switch and make some leads that connect to a 12-volt battery. So, more wraps of wire and more current means the electromagnet should be stronger.
Okay, so we're gonna try this electromagnet and we're gonna pick up this stuff right here.
Great.
Ready?
You ready?
Yeah.
3,
2, 1, go! Is it on?
Yeah.
Wow, it really does, you can't tell it it's on, but.
No, but bring it closer and.
Oh yeah, look at that. Okay, we turn it off.
All right.
Let's see if this nail can pick up this nail.
All right.
Ready?
Ready?
Go. Oh. Okay, how about this side? Oh, no. No.
I don't think we're strong enough.
It's not strong enough. I think that we need to max this out even more.
Even more?
Right.
So I'm thinking there are a lot of appliances that use electromagnets, meaning it's already set up, it already has tightly wound coils and high voltage. So we're in a lab here. Maybe do you have old appliances around?
I have parts bins with a whole bunch of stuff. Maybe
Oh.
we could find some electromagnets in those.
Let's do it.
Okay, great. Let's go.
Mini Max.
All right, pliers, battery, copper wire. Now, if you've already done the electromagnet experiment, here's another experiment that uses all the same materials plus these. Ha! Neodymium magnets, some of the strongest magnets you can get. So, here's what you need.
A battery, some neodymium magnets the same diameter as your battery, copper wire, and some pliers.
So here's what you do. First thing is you put the batteries and the magnets together like that. Then what you want to do is bend the wire so it's touching the top of the battery and goes around the battery and then touches the magnets at the bottom. Here's what that might look like. I say might because you can do any shape you want. I've made a coil here, and if you put it over the battery, you'll see it only touches the very top of the battery and the magnets at the bottom. And if I let it go, it spins. It's a homopolar motor. What happens is the battery sends an electric current through the copper wire, and that turns it into an electromagnet, which is attracted to the magnets at the bottom, and it spins. So now let's max it out. Haha, a D-cell battery, which is larger and, of course, larger neodymium magnets. And you do the same thing. Make a coil that only touches the battery at the top and at the magnet, and haha, it spins. Maxed out homopolar motor. But don't worry, this is not the biggest size we're gonna do. Come on. Maxed out homopolar motor. I have 27 D-cell batteries, a giant copper tube, and a neodymium magnet. So I'm just gonna, and then we get rid of that. Put this down. Okay, so the first thing I do is attach the neodymium magnet to the batteries. And I've got all the batteries taped together here so they'll sort of stand up like this. Huh? Giant stack of D-cell batteries. Okay, now what I do is I take the copper coil. I take the copper coil. I need to get. Okay, hold on. I got this. I just need to get the copper coil there. I did it. Okay, so I take the copper and I put it on top of the D-cell batteries like this, and then I let it go. Let it go. Nope, whoa. Homopolar motor. Okay, so that didn't work. But that's okay. I like it when it doesn't work, because that's science. It's not science if it works perfectly every time. I mean, you gotta have some room for improvement.
Heather and I built a larger electromagnet, but it still wasn't as powerful as we hoped. So now we're searching for parts that came out of an appliance that are pre-built electromagnets.
What about this?
I think that'll do the trick.
Do you think that does look like an electromagnet, huh?
It does, yeah.
And there's a whole big bunch of copper wires coiled on
Coiled
that.
around.
So you think we can use this?
Yeah, let's try it.
Okay, great.
We built the next version of the electromagnet. This one already has the copper coils, so it's just a matter of attaching wires and an on-off switch, and attaching all of it to a 12-volt battery.
Do you think 12 volts will be enough?
Let's find out. I think so.
Try that.
Once we do, it works much better.
Oh, no problem at all.
Ready?
Yep, turn it on.
On.
Whoa, pretty good. Okay, off.
Off.
Neat. In case it was really strong, I have the next step. Horseshoe. Okay. Ready? Oh, whoa. That's...
Here.
I can't pull that off. Okay, wait, grab this. Okay?
Work together.
Yep. So that's passed all of our tests.
Yeah.
This is really strong.
Is
What
there a
do
way
we...
to test it further?
In order to test how strong our magnet is, it's as easy as seeing how much weight it'll lift. Heather and I find a metal table.
All right, Phil, so I brought the electromagnet.
Okay.
Just put it right here.
Yep. We add some sandbags for more weight and then attach a scale so we can measure how much weight we're lifting. We use a chain hoist, a simple machine made for lifting heavy things. This one can hold up to 454 kilograms.
Want to turn it on?
We're ready?
Yep.
Here we go.
You can read on the scale how much weight is being lifted.
And that scale is going up.
Pounds on this side, kilograms on this side. We keep lifting until...
Oh, okay, so how much did it hold?
It held 100 kilograms.
Oh, that's more than I weigh, which gives me an idea. Come on.
This is ferrofluid. It is ferromagnetic, which means it's attracted to magnets. And I know what you're thinking. You're thinking, it's not that interesting. Well, watch as I put it next to this magnet. Very interesting. And because it's a liquid, it behaves in very interesting ways. Watch this. Unlike most things ferromagnetic, like paper clips or iron filings, ferrofluid is a liquid, which means it behaves in a unique way. The spikes it creates are following the magnetic field lines of the magnet. You can see the magnetic field in 3D. It's even more impressive when we max it out. This is ferrofluid outside of a glass jar. Now, it's sitting in a pool around this electromagnet. And this is a dial which I can use to change the voltage of the electromagnet, making the magnet stronger. Watch this. Changing the current going to the spiral in the middle turns it into a magnet. The more current I put in, the stronger that magnet becomes, allowing the ferrofluid to climb the spiral to the top. And remember, even though it looks all spiky, it's still a liquid. I will demonstrate with my plastic spoon. And watch this. When I turn the magnet off, it stops being spiky. Turn it on. Turn it off. Science.
The Wizard Academy. All you have to do is demonstrate true magic. And you will be granted entry.
Well, Fuzzix, who is the next applicant for the Wizard Academy?
Overwhelmo.
Indeed, it is I, Overwhelmo. And prepare to be overwhelmed. Would you be flabbergastified if I balanced this coin on its end?
Not really, no.
But would you be impressed if I was to balance this coin on top of this coin?
Possibly.
Prepare to be flustered and stupefied. Stupeflustered as I balance 3 coins on their ends on top of this glass.
Well, that certainly would seem like magic. Let us see.
Okay. No pressure, Overwhelmo. You can do this.
And now, I say, a magic word.
A magic word! Ha 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 ha! And now you must let me into your academy.
Wait. What's under the cloth?
What cloth? This cloth? Nothing. Oh,
Is that a magnet?
this? No.
The pull of the magnet is what's keeping those coins up. The magnet is just strong enough to keep the coins from falling.
No, this is set dressing. It's just.
It was a good trick, but it's science, not magic.
Well, yes.
And you will see! You will see! I will be back! I, Overwhelmo, will return! And I will do such magic that you will need extra socks. Because I will knock them off! With my magic, you will need at least 2 pairs of socks, maybe 3 pairs of socks.
We can still see you.
No, you can't.
So back to our main experiment. Heather and I have created a very strong electromagnet that can hold a lot of weight,
It held 100 kilograms.
Oh.
which gave me an idea.
All right, you ready?
Let's do it.
Electromagnets, super maxed out experiment. We've got,
2 electromagnets, 1, 2.
and those are wired to 2 batteries, which are on my belt, just like this, so that I can carry them around. And we've got a crash mat here because
We need to keep you safe because you're gonna be using these electromagnets to get across this massive beam above us.
that's right. I'm gonna stick to this metal beam and go across with the electromagnets.
Wow.
We hope.
I have faith.
I'm glad you do. I've got helmet for safety, goggles for safety, gloves for safety, but in this case, sometimes a lab coat is more safe and sometimes it's less safe. This time, it will get all caught up, so no lab coat. All right, you ready to go?
I'm ready. Let's do it.
Okay.
Oh my goodness. 1.
Okay.
Because each of our electromagnets can hold more than my whole body weight, I can use them to cross the beam. When they're on, they stick like, well, magnets. And when I turn them off, they stop being magnets and I can move them along as I go. Now, this is something you should definitely not try at home.
Come on, Phil. You're almost there.
We did it! Yeah! There you go, Science Max, experiments at large, electromagnets. You wanna go?
No,
You sure?
I'm positive.
Okay, I'm going again. Woohoo!
Crazy.
Greetings, Science Maximites. My name is Phil. And I am Opposite Phil. Opposite Phil. That's right. Blue lab coat, yellow shirt, evil mustache. I see. Anyway, we're looking at opposing forces today. That's forces that make things go down and forces that make things go up. Right, things with more density and things with less density. Gravity and the opposite, which is anti-gravity. Anti-gravity isn't really a thing. Well, I have to do the opposite. Right. Buoyancy. And buoyancy's opposite, which is girlancy. No, girlancy is not the opposite of buoyancy. You know, you're not helping. Right, not helping. Opposite. Haha. Hello. Goodbye. Today we're going to be making a gravity-powered boat. Ta-da! It's pretty easy to make. You just put water in the top here. Gravity of the water pushes it out the straw, and the boat goes forward. And it's super easy to make. You only need 4 things.
A piece of styrofoam, a plastic cup, craft stick, and a straw. And the tools you'll need, a pen, a craft knife, and the help of an adult, and science glue.
Which is the same as regular glue, except I only use this glue for science. You take your styrofoam and you cut it into a boat shape. That requires the knife and the help of the adult. Then take your cup and draw the circle that your cup will sit in. And then you want to put 2 slashes with your craft knife in there. Again, get the help of an adult if you need it. And then start carving out the styrofoam with your finger and make a nice little indent just like this for your cup to fit in. See? And then it fits in nice and snug. So then what you want to do is you want to make a hole in the cup. You can use a pencil. And the hole has to be just big enough for the straw to fit in. First, you want to take the straw and dig up in this direction so that it will be a nice angle for the water to come out, and then you want to get the straw back up into the cup like that, and then glue it so that it is not going to leak any water. And then in the final step, and this is your choice, you don't have to do this, but you can use your craft stick and you can make a rudder, or if you want, you can make a whole keel, which goes just like that, and it is right in the middle of the boat, and this helps the boat go straight, because sometimes the straw goes off to the side one way or the other. Okay, water-powered boat. Actually, it's a water and gravity-powered boat. You see, what you do is you fill up the cup with water, and the gravity of the water in the cup pushes it out the straw, and the boat goes forward. And this is what it looks like in the water. You fill up the cup, and the gravity pushes the water out that way. The buoyancy of the boat keeps it afloat, and good old Newton's third law, for every action, there's an equal and opposite reaction. The water going out the straw this way pushes the boat that way, and it works pretty well. Whoa, if it's going straight. That's why we have the keel. Okay, so gravity-powered boat. Time to max it out. But first, I need an expert to help me. Oh, of course, Michaela from the Ontario Science Center. Perfect. All right, and let's go. No! I stopped myself! I didn't get wet! Now I'm just gonna get... No! Oh. Hey, Michaela! From the Ontario Science Center, how you doing?
Good, how are you?
That was the best portal malfunction ever! Glad you're here, because I need your help maxing out this. The water gravity boat. It's pretty awesome, and what you do is you put the water in the boat, and then it does this, and it propels itself along. So, we're gonna max it out and make it super awesome. So what do you want to do that?
Oh, man, well, what if we just think about making everything bigger?
Okay.
Right? Like, first we're gonna need a bigger container.
Okay, well, that's a good idea. Tell you what, I got my waterproof portal ordering device. So I'll order some sort of a bin?
Yeah,
Like a big
yeah.
plastic bin. Okay, hold on.
That'd be-
Hold on. Here it comes. Oh, there it is.
Yay!
Okay, so a big plastic bin.
Yeah, and then, you see this straw here? What if we had something like that, except bigger,
Like a pipe of some sort?
yeah, like a big pipe.
One pipe coming up.
I need to get myself one of those.
Yeah, but it doesn't always work, so. Oh, here it is.
Wow.
So, bin is the cup,
Yeah,
pipe is the straw.
yeah.
So now all we need is the boat.
Yeah, the platform itself. I think we need something that's gonna be really stable, because we're gonna have a lot of weight this time.
How about like a surfboard or one of those stand-up paddle boards?
Hey, that's a good idea.
Yeah, okay, check this out. Uh-oh,
Oh, no.
water stopping.
That doesn't look good.
I think it might have gotten stuck.
Oh.
We'll have to go get it. Because the water is still running and that might overflow,
Man,
so.
it's stuck somewhere.
Buoyancy is the tendency for things to float. Things like this balloon, or this ball in water. But it doesn't float on its own. The helium is less dense than the air molecules around it, and they fall past the balloon and push it up. The ball is less dense than the water around it. So the water molecules flow around the ball and push it up. This happens because water is a fluid. The particles flow around each other. This works because air is a fluid. And I know what you're thinking. You're thinking, Phil, air isn't a fluid, but it is. Usually we think of fluid as meaning a liquid, but in this case, fluid means anything where the particles can flow around each other, and that includes air. But you know what? It's hard to see the particles in water. Same thing with air. I can say it, but it's really hard to see it. Now this is sand, and it behaves like a fluid too. Well, sort of. Check it out. Look, it's made of a whole bunch of very fine particles, and it takes the shape of its container. But watch this. I put a ball in the sand, and it doesn't float. Now, the ball is less dense than the sand, but it doesn't float because the particles of sand have a little bit too much friction right now. But watch as we move them around and reduce the friction by adding some air. Now, this sand is behaving like a fluid, and the ball floats. Let's see what else floats on sand. How about this pumpkin? Yep, that floats. How about this block of wood? Yep, that floats too. How about this styrofoam ball? Yeah, that definitely floats. Look at that. The sand is a fluid right now because all of the little particles of sand are moving around. But watch this. If I turn off the air, everything freezes in place. Nothing floats anymore because the sand is no longer behaving like a fluid. So there you go, buoyancy. It all depends on the density of the thing and the fluid it's surrounded by. Huh? Science.
Michaela and I are maxing out our gravity-powered boat. We had a bunch of maxed out materials. We just needed to get our surfboard.
So we got our giant bin,
We got a giant tube. Water's gonna come out of this end.
and we've got a valve here, which means we can fill the bucket, and then we can turn on the valve and see what happens. So, whoa.
Hey.
Okay, you ready?
Yeah,
Now we're
here
gonna turn
we
on the
go.
valve, and that means now the water is flowing through.
Ooh,
Hey, it's working.
not bad.
Right on. Whoa, look at that. This thing is really working.
Yeah, it's taking off now.
So, okay, this is good. It's going about walking speed. Now that it's working, how do we max it out?
Our fuel here is the water, so
Yeah.
what if we just had even more water?
And it doesn't last long, does it?
Maxing out our boat even more is easy. A bigger bin for more water, and a wider pipe to move more water for more thrust.
Okay, so a bigger bin
Yeah,
is a lot harder to fill because it's hard to get to the top of it.
well, you're working against gravity, so it's gonna work for us.
I can really appreciate the amount of water that we're putting into this. That's 4 buckets full.
Wow.
This is 5 buckets.
We open up the valve and it starts to go.
Yep,
Working.
it is working. Look at all
Wow.
the awesome
Check
bubbles.
that out.
Okay,
That works really well.
it really, yeah, it's definitely
Wow.
faster than the other one. I think it's the larger pipe, and we need more water because it doesn't last very long.
Check it out. It looks like it's going even faster now that we've lost a bit of the water.
Less weight.
Yeah.
This is working great, so now how do we make it even better?
Okay, well, the only force working with us right now is gravity, right? Of
Right.
the water coming out. What if we add in an extra force?
And we could squish the water down to go out faster. Okay, watery high five. Okay, we gotta get it's way over here. Come on, we gotta get it. I want to move the water from this container to this container. Now, I could just pour it, but what if it's too heavy? It's too heavy! Help me, science! Well, science to the rescue with this! A clear plastic tube! Ooh, science-y. Okay, watch this. I'm gonna make a siphon, and it's pretty complicated, so follow along. Are you ready? I stick one end in here, and one end in here! Whoa! Yeah, I know, it's not working yet, but that's because we haven't added the science. First, we need to add a little bit of suction and suck the water through the hose like a straw. It has to go over the highest point. Watch this. And there we go. Look, the water is going up. I can even make the water go up even more, and it still works. But why does the water go up? Water doesn't like to go up, right? Well, the reason why is because there's more water going down than there is going up. So that creates suction on this end, and the gravity of this water pulls that water up. So gravity is doing all the work for us. And that is a siphon. Huh? So now let's max it out. This is the same container of water, but now it's colored slightly blue so you can see it go all the way up through this hose. The only really hard part about this is sucking the water all the way up to there. Okay, here we go. I got it working. Now, the reason why it's working is because there's just a bit more water on this side of the tube than there is on this side of the tube.
With a siphon, it doesn't matter how far you go up, as long as the water on one side is lower than the other.
Science. You know about helium balloons, right? Helium is a harmless gas that is less dense than air, which is why helium floats.
If I was to breathe some helium, my voice sounds higher because helium is less dense than normal air, so my vocal cords vibrate faster. Ah!
But have you ever wondered, is there a gas that's more dense than air? There is.
It's called sulfur hexafluoride, and it's much more dense than air. So if I was to breathe some, my vocal cords would vibrate slower, making my voice lower. Ha 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 ha!
This container is full of sulfur hexafluoride. Ooh, I know, it's invisible, you can't see anything. But watch as I blow some bubbles. The bubbles are floating on top of that layer of sulfur hexafluoride.
The bubbles float because they're full of regular air, which is less dense than the sulfur hexafluoride.
In fact, a balloon will float on this as well. The balloon floats lower because the weight of the latex also drags it down a bit. But the bubbles and the balloons are floating on a sea of sulfur hexafluoride. And it is like a sea because it's a fluid just like water, but it's more dense than regular air.
Science! It's awesome!
Michaela and I are maxing out our gravity-powered boat. It was already working well, but now our idea is to try squishing out the water so it gives the boat more thrust. We just had to come up with a brilliant idea how to do that.
Garbage bag! Garbage bag! Yeah, garbage bag! Okay, maybe we should explain the garbage bag. Okay, so the garbage bag is attached to the pipe at the back end. There's a hole in the garbage bag. Whoa, we fill the garbage bag with water. Then we tie the garbage bag tight. Tie the knot so the air doesn't get it. Now that we've got that, we use bowling balls! And we put the bowling balls on top of the garbage bag, and this will, whoa, squish the water out.
Really is pushing on that bag.
Okay, ready? Okay, let's see.
Hey, it's moving.
Our bowling balls were squishing the water out, but the boat didn't seem to be moving much faster.
I think the bowling balls made the whole thing too heavy.
What if we raise the bin up?
If it's higher up, then there would be more force due to gravity.
Yeah, so we have the bin on like stilts or something,
Oh my God.
and then it has to fall further, and then maybe the water's going faster.
I love that idea.
Okay, good.
Yeah, let's try it.
So what we need to do is get
Wait,
this.
no.
Oh, I thought this is the shallow
No,
pool.
yeah, no, that's
that
over
one's
there.
that's that
yeah,
one. Yeah.
not here.
Max Historica. Long, long ago, in the time of ancient Greece, there lived a genius named Archimedes. One day he was in the tub and he noticed something.
Oh, hello. Look at that. When I get into the tub, the water level goes up, and when I get out of the tub, the water level goes down. Ha! Eureka!
I, don't get it.
Well, I can calculate how much volume something takes up by how much water it displaces.
Yep, still not with you.
Now, I'll give you an example. How much water would be displaced, pushed aside, if I put this ball in the water?
It's light, so not much.
Ah, it doesn't matter how heavy it is. It only matters how much space it takes up. Watch. Ha! You see? The same volume, huh?
I think I see.
How much water will be displaced when I put this bowling ball in?
More because it's heavier.
Ah, nope. It doesn't matter how heavy it is. It only matters how much space it takes up. Watch.
Oh.
You see? A simple and easy way to measure something's volume.
Archimedes, one of the greatest and cleanest scientists in history. Join us next time for more Max Historica. The metric system in 60 seconds.
The metric system is a way of measuring things. Water boils at 100 degrees Celsius, a kilometer is 1,000 meters, but few people realize just how interconnected the metric system is. First of all, it breaks down to a base 10 system. Everything is 10, 100, or 1,000 of everything else, and it's all based on water. This is exactly 1 liter of water. It weighs exactly 1 kilogram. It fits into a cube 10 centimeters on each side. It boils at 100 degrees Celsius and freezes at 0. And this happy little fellow is 1 milliliter. It fits into a cube 1 centimeter on every side. It weighs exactly 1 gram, and the amount of energy required to raise this 1 degree Celsius is 1 calorie. The metric system, everything interconnected and all based on water. Ha! Oh. Uh-oh. Michaela and I are experimenting on our maxed out gravity-powered boat. Trying to squish the water out with bowling balls added too much weight for it to make much of a difference. So now we've raised our tote higher up, which means the water will have farther to fall and be going faster when it comes out. And I got a totally awesome name for our boat.
Tell me, what's up?
Totes McBoats.
That's a totally awesome name!
Totes McBoats? Yes! Okay, so are we ready to fire up Totes McBoats?
That's right, yep.
Okay, I'm gonna turn on the valve. Okay, ready? And let go. Totes McBoats! What we hadn't considered is that much weight that high up would be tippy. Totes McBoats no longer afloat. We needed a way to solve the tipping problem first. You know what we need to do?
What?
We need to build an outrigger.
All right, so check it out. This time we have an outrigger, which means our boat's gonna be a whole lot more stable. It's not gonna fall that way because this thing is floating, and it's not gonna fall this way because it has a lot of mass as well. Think we're almost ready, eh, Phil?
Yeah. Okay, are you ready?
Ready?
Okay, let's do it. Turn on the valve.
Here we go.
Go, Totes McBoats. Oh, yeah.
Hey.
Yes. Yes. Totes McBoats. Oh, the outrigger's pulling it to the side. Whoa. In this way. Yes. It goes really fast. Our gravity-powered water boat worked great. The water ran down from high up, giving it more speed due to gravity, but no more mass than before. And our outrigger kept the whole thing from tipping over. Totes McBoats was a success. Thank you very much, Science Max Experiments at Large, gravity-powered boat, otherwise known as Totes McBoats! Totes, come back, Totes! Come back!